Hello, welcome to my second video on very simple CPU programming. This is Fatih Urda. We're going to write a subtract program today. So you're looking at the board from one of my earlier lectures in the a few years back. So if you look at right here, this is where I start writing a subtract program. So subtract is basically addition. It's the same as adding the negative of a number with another number. So as you may remember, all the instructions refer to basically data in various locations in the memory. So A and B are locations, and star A means the data in that location, star B means the data in that location. So every instruction has two arguments in very simple CPU, and both arguments are addresses, locations in the memory. But one of them, the second one, could be immediately a number if it's a like the little I variant of the instruction. But normally an add instruction, for example, is star A equals star A plus star B. But we want to do a subtract, so we cannot do it an add. Somehow we can do it with an add. We have to do it with an add, but somehow we have to really compute the negative of the second number. So we need to do 2's complement. So we have to remember from our digital design course, or as it is called at Özyeğin University, digital systems course, how to calculate the 2's complement of a number. So why 2's complement? What is 2's complement? So why 2's complement? Because in digital chips, including CPUs, the most convenient way to express a signed number is the 2's complement format. So 2's complement is a little complicated format, but it's easier to make circuits that use it. So from a circuit point of view, it's quite an easy, convenient format, but from a human's point of view, it's a complicated format. But since it's a circuit which is gonna manipulate the 2's complement numbers, we have to really go with what's easy from a circuit point of view. So 2's complement is 1's complement plus 1, and 1's complement right here is nothing but all the bits negated. So we have to take B and we have to somehow write here. So 2's complement is 1's complement plus 1. 1's complement is simply a bitwise negation or bitwise inversion of bits. Tilde means we're inverting all the bits of X. But bang, exclamation is logical inversion, don't forget about it. But 1's complement is really bitwise negation, so it's tilde X plus 1. So the X here is star B, so we have to really invert all the bits of star B. How do I invert all the bits of star B? So that's the question. So if I can somehow invert all the bits of B, then I'm going to add 1 to it, then I'm going to add on top of star A. So that's all there is to it. So here I say adding 1 is simply an add little I operation. I will immediately give 1 in the instruction. And adding, so right here, let's say I'm subtracting location 101 from 100. Then in that case, I have to take the 2's complement of the number in location 100, which is star 101. So somehow I have to negate all the bits of star 101, write it to star 102. I don't know how to do it at this point in time. I haven't decided or I haven't figured out yet. Then I'm going to add 1 on top of it, 1 on top of 102. So that's with it's going to be done with a little add little I instruction. Then I'm going to add it on top of 100 and store it in 100. So if I had a subtract instruction, which I don't, sub 100 101 would really mean star 100 equals star 100 minus star 101, just like an add 100 101 means it's the instruction which does star 100 equals star 100 plus star 101. So I'm going to write the sum into 100 Uh, so I'm going to take what's in 100, star 100, add what's in 102, that's star 102. So star 102, if I can do these two lines, star 102 will have the 2's complement version of star 101, which is minus star 101. So I have to really figure out how I negate all the bits of star 101. That's the next slide. I have a bitwise NAND instruction. With NAND, I can really do every logic operation. With NAND, I can do everything. With NOR, I can do everything, one or the other. With MUX2, I can do everything. These are universal gates. This is what you were taught. So when I teach digital systems at Özyeğin, I teach this, and if you took it from somebody else, you were possibly taught this. Believe me, even if you don't remember. So how am I going to do a NOT? If I feed the same thing, I'm going to do invert bits of A and obtain A prime or tilde A. I need to feed A to both inputs of NAND. So if I bitwise NAND A with itself, I get A inverted. So in this case, I'm going to input star 1. So let's do this. It's better because if I do feed 101 to NAND, if I did NAND 101, 101, all the bits in 101 would be inverted and 101 would be modified. But if I want to do star 100 equals star 100 minus star 101, this really means I'm not overriding, I'm not really modifying 101. So I better copy it to a scratch location. So CP 102, 101 will create a copy of the number in 101 in location 102. When I do NAND 102, 102, it's going to AND 102 with itself. If you AND something with itself, you get itself. But this is a NAND, it's not an AND, so there is an inversion after the AND, so it will invert 102. So this inverts all the bits in 102. But all the bits in 102, they were equal to the bits in 101. So in 102, I have the not of inverted version of 101. That's one complement. If I add 1 to it, normally adds the number in location to the number in this location. But if it's add little I, this is not an address, this is a number. So it adds 1 on top of the number here. So this number was 1's complement of 101. Now it's 2's complement of 101. So that's really, according to 2's complement notation, representation, it's the negative of star 101. So in 102, I have now minus star 101. So subtracting A minus B is equal to A plus minus B. So I'm adding the minus of star 101 to 100. So star 100 plus star 102 will be equal to star 100, but star 102 contains minus star 101. So only 4 instructions. What's the 5th instruction for? In our simulator at VSCPU2.org, if you really just stop writing instructions, after the last instruction you typed, the simulator version of CPU stops, because in the simulator every location in the memory stores all zeros. So if you do not have an instruction in a location, so if I only wrote 4 lines of program, a 4-line program from 0 to location 3 in our simulator at verysimplecpu.org, and also our command line simulator verysimplecpu.exe may be similar. So it hit an instruction with all bits 0, and that instruction is treated in a special way in the simulator, so it stops. But in real life, the memory may not really come up at all zeros, and implementing, like treating an instruction with all bits equal to 0 will require just unnecessary hardware. So instead, we put an explicit stop instruction here. We don't really have a separate stop instruction. A stop instruction is an instruction which does not progress any further, which stops. So it's really an instruction which jumps back to itself. So it's a BZJI instruction. BZJI is what other people call jump. BZJI jumps to an address which is stored at this address plus this number. This is 0. So it really jumps to star 5. Star 5 means the number at location 5, which is 4. So jumps back to 4. So except for BZJI and BZJ instructions, program counter is incremented, but if it's a BZJ or BZJI instruction, the instruction itself determines the next value, the new value of PC. So this program will go into an infinite loop at 4. If the CPU receives a reset, it will go back to 0 and start executing the program again. So this is the subtract program. This is all there is to it. Let's see what's next. Next we trace this subtract program, but I will do it at a different time. Okay, thank you for listening. Bye.